we're done trig, and now we move on to trig. Again, please, if there's any questions, tell me. Lecture 1.8. Trigonometric Functions, Part 2. Okay, we're going to fit a sinusoidal model to some data. We're going to sketch a bit. We're going to talk about trig identities briefly, and then we're going to talk about inverses. Okay? Okay, I just put up slides this time. If you guys are upset by that, let me know. But it's kind of tricky to try to do a PDF and slides. Yes? All right. Go ahead.
Like positive 3 over 5.
Say that again, please.
Positive 3 over, oh no,
That's all right? Okay. Okay. All right, so this is what I was doing last night. I was copying data from tables into Excel. This is the day length, or the hours of daylight, in Waterloo from January 1, 2014 to yesterday. Okay, and what we're going to try to do, you can call this modeling if you want. And what we're going to try to do is, so, yes? Yeah. Yeah, okay, so remember negative angles are measured clockwise from the positive x-axis. So 0 is here, minus pi over 2, minus pi. So if I say theta is between minus pi and 0, then that means that I've got to be down here. Does that make sense? All right. Okay. Okay, again, this is the hours of daylight in this city for the past few years. And we're going to try to model it. And this should be a good example because if you're a physics person, this is astronomically significant. And if you're a biology person, a lot of stuff depends on photoperiod, so this is significant. So there you go. This thing looks periodic, yeah? It looks periodic with period a year. It looks pretty sinusoidal, so let's try to model it by a sinusoid. Okay, let's try to model it by a cos for no real reason. Okay? You could use the sine. Alright, so L would be the hours of daylight, or the length of the day. T would be the day since January 1, 2014. And we have to find A, B, C, and D. Okay? And I put a minus sign in front of C to make our lives easier. Okay, and also to make our lives easier, we're going to work on this so that A and B are positive, so that we don't have to flip stuff. Okay? But note that if you had negative A, that would mean that the graph of cos would flip like this. And if you had negative B, then the graph of cos would flip like this. Okay? And that would change nothing, that second one, right? Flipping a cosine horizontally does nothing because it's even. Okay. And for the record, I'm going to show this the way I thought about it, but there's another way on Mobius, so you could look there, or you could ask me about that, or I could do it in the tutorial. Okay? In case this way doesn't work for you. Okay, so suppose we have a cosine. Okay, we got 0 there, we got 2 pi there, we have minus 2 pi there, 1 there, and minus 1 there. Y, what we couldn't call this? Whatever, x. Y equals cos x. Okay? Alright, so when I transform it like that, what does the graph of L look like? Okay, so first we do, again, I'm going to rule out flips for this. First we do all our scalings, okay? So we vertically scale by A. So this thing stretches by a factor A. So the amplitude changes from 1 to A. Does that make sense? Okay, I stretch it by a factor A, so the amplitude changes to A, which is what that first point says. Second, I compress by a factor B, okay? So I compress by a factor B. So the period, which was 2 pi before, changes to 2 pi over B. And that's what the second point says. Okay? Then I do my shifts. That plus D means I shift up by D units. Okay? So this guy, after I've done all my scalings, moves up by D units. So its mean level, this sort of middle line, goes up to D. Okay, and finally, I shift horizontally right by C. Okay? Now once I've scaled and I shift this thing, the peak, or there's going to be a peak, not at 0 anymore, but C units to the right, so at T equals C. Does that make sense? Okay, and obviously there's going to be more than one peak. There's going to be infinitely many peaks, but there's going to be one of them at T equals C. Okay? Okay. If this was a sine, what would change? The first one wouldn't change, the second one wouldn't change, the third one wouldn't change, and the fourth one, the peak of sine, once you scale and do all that stuff to it, is going to be 1/4 period in, okay? So there's going to be a peak at C plus 1/4 period. Okay, for sine, you'd get, that last point would be C plus 1/4 period, not just C. But for cosine, your peak is right at 0, so life's easy, and you just shift it from 0 to C. Does that make sense? All right. Here we go. Let's try to figure out what these numbers are. Okay, so I've annotated that thing. Okay, so the amplitude is from the mean line to the peak, or from the trough to the mean line. Okay? So that's just this distance divided by 2. And we said that A was the amplitude, so there we go. A is equal to 15.4 minus 9. And I'm going to abuse significant digits here. Okay, 15.4 minus 9 divided by 2 to get the amplitude, and that's 3.2 hours. Okay, so that just says that from here to here is 3.2 hours. Okay. What's the mean level? Just right in between these two, yeah? So 9 plus 15.4 divided by 2. Okay, so right down the middle, that's the value we're at, and that's D. Okay, good. What's the period of this thing in days? 365 would make sense, right? Okay, and if you subtract those numbers, you'll get something like 365. So let's say the period is 365 days. Okay? So B is 2 pi divided by that. B is 2 pi divided by 365 days, or approximately 0.0172 inverse days, or reciprocal days. Okay? Yeah, and you can, again, like I measured it peak to peak, or using my brain, or you can do it trough to trough, or, yeah, let's say you can do every other crossing of the mean line. Okay? Period is 365 days. And finally, let's find a peak. Any peak will work. Let's pick this one, 172 days in. Okay? And we said C is the time of the peak, so let's just use that. C, 172 days. This number would also work, this number would also work, this number would also work. Okay? And we're done. And look at how beautifully it fits. Okay? The curve, the model is the red guy, and the blue guys, which you can barely see hidden behind, are the data. Okay? Any questions? We're good? Yes?
So for the modeling, like for sine actually,
Uh-huh.
why do you have to add 1/4?
Okay, so suppose you did all your suppose you did all your scaling and stuff, okay? So the amplitude changed and the period changed and all that stuff changed, right? And now you want to find out where this peak ends up after you finish transforming with your shifts, okay? So you've done all your scaling and now you want to do your shifts. That minus c means that you shift to the right by c, okay? The sign is going to start out looking like this with a peak 1/4 period in. If you shift to the right by c, the peak winds up c plus 1/4 period in.
Okay, so that's how it's going to be reflected on the graph, not the equation, right?
Yeah, in the equation it'll show up as minus c, and in the graph, yeah, the peak will be at time c plus 1/4 period. Is that okay? Okay? All right. Trig identities. Okay, point 1. An identity is something where the left side and the right side of the equation hold for all values of the argument, okay? So no matter what theta, for instance, I put into that first guy, that'll work, okay? As opposed to an equation which only works perhaps for some values, okay? An equation would be write this and then you have to solve for theta, okay? But an identity always holds true. Let's see. Let's look at it. You've seen, I think, all of these before. This says sine is odd, this says cos is even, this says they're both 2 pi periodic. This says that cos is sine shifted to the left by pi over 2, and that pretty much says the same thing. Okay?
Do we have to memorize all these or?
You did a cheat sheet, don't you?
Oh, okay.
Yeah. Yeah, so I think that, although some of this you should internalize. Okay, Pythagorean identity, which we talked about. If you divide everything in here by sine squared, you wind up with this guy. If you divide everything in here by cos squared, you wind up with this guy. Okay, so those are 3 forms of the Pythagorean identity. Also, identities are all the definitions of like the reciprocal trig functions and the tangent function. Those are also identities. Questions so far? Okay, slightly sexier things. Oh, it's all posted. Okay? Okay, so more trig identities. These are called the addition or sum identities or formulas. What can I say? Understand them, be able to use them. Okay? And put it on the cheat sheet. Just put it on the cheat sheet, don't understand them. Okay? I didn't say that. From the sum ones, you can get the subtraction ones, okay, by just plugging in something like minus beta and then using the odd even property. From the sum identities, you can get these guys called the double angle identities, I hope. Called the double angle identity by just subbing in theta and theta. So you get theta plus theta equals 2 theta, and then just stick theta in everywhere and see what you get, and you'll wind up with this. Okay? Similarly for cos. So these are the double angle formulas. Okay? By combining this thing with the Pythagorean identity, you wind up with these two guys. And by rearranging these two guys, you wind up with these guys, called the half angle identities. Okay? And that's it. And if you want to rewrite this as cos squared theta over 2 equals stuff theta, okay, you can do that. Okay, so you can replace theta by theta over 2 and 2 theta by theta if that makes you happier. And it makes it look more like a half angle like that. Okay? Yeah?
For the period in the last question, why is it the -1?
One more time. Oh, why is it to the -1?
Yeah.
The period isn't. Okay? The period's days.
Sorry, why is B the
Why is b the -1? Well, a few reasons you can think of. One is that you end up with b times something that is units of time, and cosine can't take units, so this better be in reciprocal days, so that the units cancel out. That's one way to think about it. The other way to think about it is that b was equal to 2 pi over the period. So you divided by the period, which was in days, so again, you get reciprocal days. All right. Okay, does this make sense? To some extent. Again, they all come from those first two. Okay. Yeah, identities can be very useful in calculus. For instance, if you know anything about integrals, you can look this up for fun. Trigonometric substitution. Okay, you don't have to write that down. Okay, you can look that up if you know about integrals already or if you're interested. Or take 128. Okay, so again, in really weird places, you can use these kinds of identities to make life possible. But for now, let's talk about graphing. Unless there's a question. I'm not going to do this first. All right, example. Let's use an identity to graph something. Graph y equals sine pi x over 6 times cos pi x over 6. And let me go back. Okay. All right, we want to graph this thing, but this is cryptic and weird, and yes.
Are we going to be tested on trigonometry?
What, like proving stuff?
Yeah.
I don't think so. I'll write that down as well. Okay. I don't think so. Here, maybe I'll remember. I don't think that's the point. I think the point is to be able to use them, for instance, for graphing, or possibly later for other stuff. Okay, be able to use them. I don't think those things where you write like 16-line proofs of things being equal, I don't think that's the point of this course. So you should be all right. Okay? I'll look into it. Anything else? Okay. All right, so this is a weird looking thing. How do we do this? Just take the two graphs and multiply them seems like an unappealing strategy. Or you could look over there and go, hey, that looks like something. It looks like that third line there, right? Okay, except without the 2. So let's rewrite this. 1/2 times 2 sine pi x over 6 cos pi x over 6. Okay? If you want, you can write theta equals this, and then do the stuff, and then sub it back in later if that makes your life easier. Okay? But you don't have to. Okay, so that looks a lot like the third line now. So let's just use that. 1/2 sine 2 times pi x over 6. Okay? And now we got something nice. Okay, that's something we can graph, right? Okay.
Wait, so the third equal sign is like you converted it to one of these like trigonometry.
What's that?
That's what you did, like you converted like
From here to here, I use the third one there.
yeah.
That's it. Okay? All right. If these two were different, this would be hairier, okay? But they're the same, so life's good. Okay, good. So let's start with sine. Yx. Okay, period 2 pi. Goes from -1 to 1. Okay? All right, what do we need to do? Mercifully, there's no flips. There's also no shifts. Okay? This thing says compress vertically by a factor of 2. Okay? So the amplitude becomes 1/2 instead of 1. And what does this guy say? This guy says compress horizontally by a factor of pi over 3. Okay? The period of sine is 2 pi. Like before, the period of sine is 2 pi, so it becomes 2 pi over 3. New period. 2 pi, which is the old period, divided by the compression factor pi over 3. And again, if you don't like this method, I'll show you something else if you ask me, or a tutorial, or there's another one on Mobius, okay? Okay. Again, old period divided by compression factor gives us the new period. The pi's cancel, and we're left with 6. And like I said, the new amplitude, instead of 1, becomes 1/2. New amplitude becomes, amplitude becomes 1/2. Okay, and there's no shifts, there's no flips, or anything like that. All right, easy peasy. Okay, let's call it x and y. And again, this was the graph of y equals sine x. And this is the graph of y equals all that stuff. That stuff, okay? All right, period is 6, so that's 6, that's -6, that's -3, that's +3, and that's 0. And the amplitude is 1/2, so that's -1/2, and that's +1/2. Okay? And that's it. Okay, if there was a minus sign in front, then you'd flip the whole thing. And if there were shifts, you'd do the shifts. Yes, sir.
That bracket looks like it's like pi by 3.
Can you say that one more time?
The bracket after sine, but like why isn't that?
This thing?
Why isn't that a horizontal stretch instead of compression?
Why is it not a horizontal? This is a horizontal compression or stretch. It is, yeah? So this is compressed by a factor of pi over 3. And that's why the period, instead of 2 pi, now becomes 2 pi over pi over 3. Okay? So if I said compress it by a factor of 2, the period would be split in 2. Does that make sense? This is exactly the same thing, except it's an uglier number. Does that make sense? If I'm not actually answering the question, let me know. Okay. All right, we're good? And again, scribble means this or this. Okay? Because I'm lazy. All right. Again, there's a thing in the Mobius lesson that says the way you can do this is what? To sketch sines, you can write a line where the peaks should be and a line where the troughs should be. Identify the points where the maxima should be. Draw points where the minima then should be, and then connect them all with a curve. Okay? And if you want elaboration on that, either look there or ask me. All right, let's just look at one more. I'm not going to go through this. I've written all this stuff in detail there, so you can have a look at that. If we wanted to graph y equals sine squared, again, that's a funny looking thing, so let's try to turn it into something we can graph. And using those identities, y equals sine squared is the same as y equals minus a half cos 2x plus 1/2. Okay? And so you do all the shifts and stretches and flips and stuff, and you can look at that on your own. I've written everything out, and you wind up with this puppy. Okay? And this behaves as expected. Okay? This is what you'd expect sine squared to look like. You'd expect it to be non-negative, and it is. You'd expect it to hit 0, exactly where sine hits 0, and it does. You'd expect it to go from 0 to 1, and it does. It hits 1, exactly where sine hits 1 or minus 1. Okay, and notice that the frequency of this thing is twice the frequency of this thing. Okay? Yeah.
Okay, so if it's pi over 3,
Yeah.
is that not a stretch because it's less than 1?
Pi over 3 is, first of all, it doesn't matter really, but it's a compression because pi is 3.14, so it's a bit more than 3.
Okay.
So pi over 3 is a bit more than 1. It doesn't matter, right? A compression by k is the same as a stretch by 1 over k, right? So, yeah. It's just barely a compression. 2 pi is very close to 6. Okay? All right. Questions? Alrighty. Occupy yourselves for a second. This is how Marco Rubio drinks, if anyone's seen that clip.
Like the one the president laid out tonight. The choice isn't just between big government or big business.
Okay, inverse trig functions. Inverse, in quotes, trig functions. All right, not knowing how these things work means you might be an idiot when you use your calculator, okay? You want to know how these things work and what they're actually giving you, otherwise you're just guessing on a calculator, okay? All right, so suppose we want to solve something like sine theta equals 0.6. Now, when would we want to do this? Suppose we have a satellite and we want to know when it's a certain distance away from a planet. Suppose we have alternating current, like the stuff coming out of there, and I want to know when it's reaching a certain voltage. Okay, it's important to solve these kinds of things. So how do we do this? Well, this thing really isn't one-to-one at all, right? In fact, for this particular equation, we've got 2 solutions per period. Okay? So we can't just invert the whole thing and expect that to save us. So what do we do when we can't just invert the whole thing? Restrict the domain, and that's what we're going to do. Okay, so we're going to restrict the domain of sine such that we have a piece that's one-to-one and covers the whole range. Okay, and we want to cover the whole range so that we can answer any question we get given. We don't want to be missing stuff. Okay, so cover the whole range and get something one-to-one by restricting the domain. And then invert that, use that to solve your problem, and then find all the solutions you need using symmetries and periodicity and that kind of thing. Does that make sense? Shake your heads like wildly. Okay, good. All right, where would this thing be 1 to 1? Where could I cut this thing off?
Negative 3 pi over 2 to
Negative 3 pi over there?
to half pi, or to negative pi over 2.
To here?
Yeah.
Yeah, that'll work. That works. That also works. And that's the one we take. Okay? Minus pi over 2 to pi over 2. Yours works too. Okay? So for... Wait, what do I want to say anything else first? No. Okay, exactly. So let's restrict this thing to minus pi over 2 to pi over 2. Okay? So we'll restrict the sign to its domain to minus pi over 2 to pi over 2, as is stated about 20 times there. And that gives us something that's 1 to 1, and it gives us something that spans the range of sign. Okay, and now we can invert this, and we do, and we get this guy. Okay, and this function is called the inverse, quote-unquote, sine function, or the arc sine function. Okay? Inverse, quote-unquote, because what? Because we haven't actually inverted the sign, right? You can't invert the sign. We can invert it on a restricted domain, and that's what we've done. Yeah?
Sorry, what do you mean by 1 to 1?
Say one more time.
What do you mean by 1 to
1
1?
to 1. So, invertible, it passes the horizontal line test. Does that make sense? Yeah. Okay? All right. So again, this obviously passes the horizontal line test, right? And it spans the range. So again, we flip it, and we get this guy. Okay? I've tried to be friendly here. You won't always see this. I've tried to use Z for trig values and theta for inputs to trig. Okay? Hopefully that alleviates some confusion, but you won't always see that. So they could be X and Y. Okay. Does this make sense? All right, the domain of this thing now is minus pi over 2 to pi over 2. The range is minus 1 to 1. So when we invert, we get the opposite. Okay? The domain here is minus 1 to 1, and the range is minus pi over 2 to pi over 2. So for arc sine, the domain is minus 1 to plus 1, and the range is minus pi over 2 to plus pi over 2. Again, I'm going to say again, this thing, quote-unquote, inverse sine or arc sine, this minus 1 does not mean take the reciprocal. Okay, life's not that easy. What else? You've got a definition there that essentially tells you that the arc sine of a number is the angle or number in that restricted interval that gives you that sign. Okay? Kind of sounds like the definition for inverses in general, kind of sounds like the definition for logs. Okay? So however you understand it, make sure that makes sense. Okay so far? Please tell me if you're not okay.
So you just explain that one more time.
That's it. That last thing I said?
Yeah.
Yeah. Okay? So the arc sine of a number z is that theta which produces that sign value, but is in that interval. Okay? And crucially has to be in that interval. Okay? So we get a unique answer. And so your calculator acts in a predictable, nice, lovely way. Okay? Okay. These are the cancellation equations, the inverse undoing the function. But notice, again, these guys aren't actually inverses, right? This is only the inverse of this guy on a restricted domain. Okay? So the cancellation only works on that restricted domain. Okay, does that make sense? Inverse undoes the function, but only on the proper domain. That's all that says. Any questions at all? And notice the function's increasing, so its inverse is increasing. No questions? Do I have any questions? I do have a question. Okay, example. All right, what's sine inverse of minus, I'm going to write it like this time, minus 1 over root 2. Okay, we sort of did this before, right? We did this earlier. Unit circle. Okay, we want to find that angle that gives sine value minus 1 over root 2. Okay, and before we solved sine x equals minus 1 over root 2, so this looks similar, right? So to get it, yeah, I think. Yeah? So for the sign to be negative, we got to be down here somewhere. Okay? But remember, you have to pick something between minus pi over 2 and pi over 2. So that's here. So you've got to be down here and here. So that means you've got to be in here. Okay? So not 2 solutions this time, but just 1. And in fact, we had infinitely many solutions last time. Okay. Minus 1 over root 2, if I want to stay in the unit circle, plus 1 over root 2. Okay, and what is this angle? Minus pi over 4. And that's the answer to it.
So we can just ignore the sine -1 and just treat it like a regular problem.
You're answering the question, sine of theta equals this. Okay, so the opposite on the proper interval. Okay, again, you're answering what is theta for which sine of theta equals this, and theta is between minus pi over 2 and pi over 2. And this guy works, right? It's on the right interval and it gives the right sign. Yeah?
Should we include 2 pi n plus 2 pi n?
No, right? Because that takes you out of the interval. Okay? If you add 2 pi n, you're not between minus pi over 2 and pi over 2.
okay,
Yeah? So it's only ever going to have one answer, yeah?
So then what would we do if, let's say, it was in a different, like if it was in like 3 pi over 2, and then 5 pi
3 pi over 2 is here? 3 pi over 2. Over here?
Yeah.
Yeah. That still works, right? That's still between minus pi over 2 and pi over 2.
Yeah, so I'm saying like if
You're over here or something?
yeah, if the domain is like it's
It'll
still
always work.
restricted.
There'll always be a value that works. For instance, this guy, you could have also thought, well, this will work, okay? Because this guy also has sine back.
Yeah.
But this isn't in the range. I mean, this isn't in the range, but this guy is. Yeah? So there's always something that'll work. Okay? So there'll always be one value that works. You've got to find that value. Is that all right? Okay. Same deal with cos. We've got to restrict it so we can invert it. Okay? What are we restricted to? We can't do minus pi over 2 to pi over 2 for cos because it looks like this. Okay, that would be stupid because we not only don't get the whole range, we also don't get 1 to 1. So that's no good. So for cos, we restrict from 0 to pi. And that's what that shows. And we invert to get this. And exactly the same story as I said before, okay? Yes, ma'am?
For the example that we just did with sine, and then the previous example we did where we could have written it as 7 pi over 4, can we do that as well?
Yep. Can we do this as well? Again, only one possible answer. So 7 pi over 4 does indeed give that sine value, but it's not in the right interval. Does that make sense? There can only be one Lord of the...
There is only one Lord of the Ring.
There can only be one value that lies in the interval. Okay? Which is kind of the point. Okay. We're good? That's cos. Again, restrict to somewhere appropriate. In this case, from 0 to pi. Same story. Be careful with cancellation and understand what that means. Okay? And again, we'll get the graph of the inverse by flipping over y equals x. And look, they're both decreasing. Isn't that nice?
Sorry?
Finally, arctangent. Same story. Restrict so you get the whole range, and you've got something 1 to 1, i.e. it passes the horizontal line test, so you can invert it, and you invert and you get this. Okay? In this case, what do you have to restrict to? The open interval from minus pi over 2 to pi over 2, which in this case actually covers a whole period. Okay? Make sure you see why that covers everything. Make sure you see why that's 1 to 1. Also, I would add the domain and range of arc cos. Almost done. Say again, please. One last time. Is it like the arc sign? Almost, but you're missing these 2 points. Because they're undefined here, right? So it's almost like arc sign except missing these 2. Yep. Okay, arc cos. I just want to say the domain and range. Arc cos, which you can read off of the graph. The domain, again, is from minus 1 to 1, which is the range of cos. And the range is from 0 to pi, which is the domain of the restricted cos. Okay? So again, find the right value, make sure it's in this interval if you're evaluating arc cos. This guy again, quote-unquote inverse tan, or arctangent. We restrict to the open interval here. because it spans the range and you've got something 1 to 1. You can flip over y equals x to get the graph of the inverse. It's called arctan or inverse tan. Be careful in cancellation that you're in the right interval. And everything else is the same kind of story, okay? 2 more observations. We have vertical asymptotes here. When you flip, you get horizontal asymptotes here. And final thing. Almost final thing. At most half a minute, people. Arctangent. What's the domain? I'm not going to be able to hear your answers anyway. What's the domain of arctan? Everything, in the same way that the range of tan is everything. And the range is just that restricted interval from minus pi over 2 to pi over 2, excluding those endpoints. Okay? Final observation I'm going to make, I promise, is this. If you consider something like arctan k theta, and just as I'm obvious, I'm going to tell you. Okay? What does the graph of this look like? It looks like the graph of arctan compressed by a factor k. So if you make k big enough, this thing compresses, and we get something that looks really, really steep here like that. And you can think of that as a switch, okay, that's continuous. Okay? Any questions? You're free. Thank you, everybody. Have a wonderful week. All right, here we go. Example, compute. Because I want to sound cool. Sine of arctan of minus 3. And I do a lot of examples with minuses, so you watch me do them as well, and you don't have to just see me do the easy pluses and then you get confused by the minuses, okay? All right. So what am I asking for here? I'm talking about an angle whose tangent is minus 3, and the angle is between minus pi over 2 and pi over 2 exclusive, and I want the sine of that angle. Now this is really similar to something I asked last time, okay? What did I give you last time? Last time I gave you the cosine of an angle, and I gave you the interval that angle was on, and then I asked you for the tangent. This is an incredibly similar problem, okay? It just doesn't show all of that. Okay, you should be able to read this and realize this is exactly the same kind of problem. I've given you the tangent of something. This implies an interval in which that angle has to be, and I'm asking for the sine of that angle. Okay? So here we go. So let theta be this thing. Let theta be that angle. Okay? And what does that mean? That just means that the tangent of theta is minus 3, and theta is on the right interval. Minus pi over 2 to plus pi over 2, excluding both of them. Okay? All right. Y, X, circle. Again, this won't be a unit circle. Okay? And I'm looking for a negative tangent. Where's the tangent negative? It's negative here, and it's negative here. Okay? Why? Because here the sine is negative and the cosine is positive, and here the cosine is negative and the sine is positive. So here and here the tan is negative. What does this tell me? It tells me to live in here. Okay? So to be here or here and here means I have to be in here. So that's where I'm looking. Alrighty. Does that make sense so far?
I'm sorry, how do you define that you're supposed to be in the...
In here?
Yeah.
Okay. One, the tangent is negative. Either using what you know about sines or cast or whatever, that tells you that you've got to be either here or here. Okay? This thing tells you that you've got to be here. Does that make sense?
Okay. Yeah.
Right, so you've got to be here or here, and you've got to be to the right of the y-axis, so that lands you in this quadrant. Okay? All right. Tangent is minus 3. Think about this however you like. Toa. Oa. Opposite. Oh, I said it right big. minus 3 over adjacent, and we'll call that 1. And this is our angle. Does that make sense to everybody? Okay, not this angle, that's out of range. Okay, not turning 100 times and then coming here, that's also out of range. Okay, this angle. Okay? All right. Okay, so you can think of SOHCAHTOA, or in a not unit circle, you can think that the tangent is the y-coordinate over the x-coordinate, the y-coordinate minus 3 over the x-coordinate 1. Okay, minus 3. Good? Okay, or if you want, you can do this in a unit circle, but I think this is nicer. Okay. All right. How do I get this length? Pythagoras. Okay. That length squared is 1 squared plus minus 3 squared, so 1 squared plus 9, so 10. So this length is the square root of 10 by Pythagoras. This length is the square root of 10. Okay? All right. And what are we looking for? We're looking for the sine of theta. Life's good. Okay, so O over H, O over H minus 3 over root 10. And that's what we're looking for, that's the answer. Okay? Again, you can think O over H, or you could think that in a not unit circle, the sine is the y-coordinate divided by the radius, y-coordinate divided by the radius. Yes, ma'am?
In assessments, do you care if we rationalize?
You say that one more time.
In assessments, do you care if we rationalize the denominator?
Almost surely not. No, unless we tell you, and I doubt that we'll tell you. Okay. Yeah.
Where did the minus pi over 2, that one come from?
This thing?
Yeah.
Let me ask first, the thing that I didn't do, right? You're asking me if you need to do the thing that I just didn't do. Is that right? So if I'd done this properly, I'd have written like 3 root 10 over 10 or something? Yeah. Yeah. No, not required unless we tell you, and I doubt we'll tell you. Okay, well, where did this come from? In the definition for arctan, you have to constrain to this. So if you look at the slide for that, it'll say this. And again, you want the whole range, and you want it to be 1 to 1, so that's the domain you constrain tangent to before you invert it. Good? All right, I'll give you one to do on your own, and if you want a tutorial, you can make me do it. Mario. Compute. Arc cos, or quote-unquote inverse cosine, of the cosine of 11 pi over 3. Okay? And that's to make sure that you don't do one illegal thing and also another sketchy thing. Okay? So try that, see what you get, and ask me in the tutorial if you want to do it. Any questions?